Hello and welcome to our 26th Virtual Research Cafe 10.0. I'm Frank Gomez, Executive Director of STEMnet here at the Chancellor's Office. Behind the scenes, we have Monica Locon, Operations Analyst, and Jesus Perez. Much thanks to her for working on the logistics and in publicizing today's event. The goal of the Cafe is to help foster collaborations across the CSU and catalyze submission of joint proposals. The Cafe brings together CSU assistant profs to share their work in a relaxed setting for 10 minutes. We hope you'll find opportunities for collaboration and or learn about a new area that may impact your own program. Feel free to contact any presenter in the chat box when they're not presenting. At the end of the presentations, we'll all come together for a Q&A session. So let's begin. Once again, we have three wonderful speakers presenting a snapshot of their work. Our first speaker is Nabila Tanjeem from Cal State Fullerton in the Department of Physics. Nabila, the floor is yours.
Thank you for the introduction. I'm really happy to be here and would like to learn your thoughts about my research. So I am Nabila Tanjeem and I am like assistant professor at Cal State Fullerton and I'm also in the physics department. So here is a little bit of introduction. So I actually joined Cal State Fullerton from last year, so it hasn't even been 1 year. And here, this is my first time living in California. Here are all the places that I have lived before. So I grew up in Bangladesh, and then I did my undergraduate at the University of Tokyo. Then I moved to the US to do my PhD at Harvard University. And then I did a 2-year postdoc at University of Colorado Boulder. And so now I'm here. So my research is in the soft matter physics, and I mostly do experiments with a little bit of computations. So what I'm really motivated by is the many exciting applications that we can realize by designing responsive soft materials. So what I'm talking about here, so I'll show a couple of videos to give a background. So here is a video of a shape-changing pasta. So these researchers at MIT, they have designed pasta that can change different, that can take different curvatures. So you can design the curvature into the pattern that you have in this material. So you fabricate them flat and have some patterns that determine their swelling behavior. And once you put them in water, depending on the patterns, they adopt different kind of curvature. And there are also many interesting applications in the biomedical science. For example, people have designed microscale machines that can grab and move cells. So here is a machine that just moved in and it's trying to hold a cell. And as you increase this temperature, it will become like a gripper, so it will hold the cell. So it's start happening now. And then once we apply another magnetic field, you can move the micro machine again. So the idea is that you want to use different kind of stimuli to impact materials, right? So what you have seen is that you can use temperature, magnetic field, light, and so on to basically achieve some kind of shape change. So the material changes its shape, or they can also move from one place to another. So what I am interested in is realizing is, can we make these responsive materials using self-assembly? So self-assembly is a thermodynamic process where if you had designed different interaction between very small particles, it could be molecules, it can also be microscopic like colloidal particles. They assemble into different structures that minimizes its free energy. So, and if you want to make responsive material using self-assembly, what you need is responsive particles, right? And that's like two different fields that are being very popular these days. One is active colloid. So the idea is that you design a motion of a microscopic particle. So for example, if you shine light, the particle will start to move. And there is another growing area where you can change the shape of these tiny little particles that could be a few microns large. So it can either like change its volume or maybe do some more complex shape shifting, like go from a sphere to an ellipsoid. So I want to like combine this like smart colloidal particles into self-assembly and then try to understand if we can assemble responsive materials from their building blocks. So a little bit of background of my previous research. So I worked a lot on self-assembly. So here you can see some like small colloidal particles. The size of them is about 700 nanometers. So you can still observe their dynamics with an optical microscope. And they're so tiny that they're experiencing this Brownian motion. And using that, we can self-assemble them into structures. So there are many different applications of self-assembly. One of them is the structural colors. So you can design different kind of colors based on what structure you make. So here is an example of what I did previously is assemble crystals out of these colloidal particles. So you can design some attractive interaction on them and you can grow this crystalline layer over time. So that's this kind of self-assembly that I'm talking about. And so now let's move on to the next step is like, can we make the self-assembly responsive? So recently there have been quite a few interest in that area. And what I'll show you is only a theoretical prediction. This has been done by the Sharon Glosser's group who do soft matter theory. So the idea is that if you self-assemble a crystal, like in the last video, and if you can address the size of each individual particle and you can change their size dynamically, what you can do is that you can create some defects that can migrate over time and change the shape of the entire structure. So here they have proposed they have done some simulations and they're showing a video is that by changing the shape of these yellow regions, they can cause a shear deformation of the entire structure. So their group is still doing a lot of studies, like what kind of shape change do you need in order to understand different kind of shape deformation? And the idea is that you can make some gripper robot by using this phenomena where you can see these tiny robots that can potentially hold an object, right? It opens like a scissor and then it kind of holds a cell in them. And we're talking about very small particles, right? Like about a micron size. So potentially this can open up a new field of designing responsive microscale structures if we can realize them. So that was all theory and experiments haven't done yet. So that's what I really want to do as my first project here. So the experiments that I am pursuing right now is I'm trying to make some colloidal particles that change their shape if you shine light on them. So light is very convenient because let's say you want to change temperature, right? You cannot really change temperature locally. But for light, it is very easy to only shine light on a certain number of particles. So that gives you the advantage of realizing the kind of application that I have shown before in the last video. So the idea is that I want to make these colloidal particles based on hydrogels. So microscale hydrogels, we call them microgels. So they're hydrophilic and thermoresponsive polymers. So at high temperature, they go through a volume phase transition and they shrink. And the way to make them light responsive is to incorporate some gold nanoparticles. So we want to decorate the microgels with the gold nanoparticles here. And we want to make a hybrid microgel. So the microgels will have a lot of gold nanoparticles on them. And then once we shine light, the gold nanoparticles will absorb light and then it transform into heat and the particle will change shape. So there have been demonstrations of making these particles, the chemists have done a lot of work before. So that part is not really new, but using it for self-assembly and understanding how we can change the shape of a global structure. So that's something that haven't been done before. So fortunately, I also received like a NSF grant very recently. So this is for new investigators from non-R1 universities called the Engineering Research Initiation Grant. So as you can see, this idea is kind of, being popular. And so I have started then doing some experiments. So we have fabricated some microgels with a size of about 2 microns. So you can see them moving around under a fluorescent microscope. And for gold nanoparticles, we can also synthesize them in the lab, but they're so tiny, we can only, we don't have the electron microscope here, but we can measure the UV visible spectrum to see that they are actually showing the surface plasmon resonance of their particular size. And you can also see that they have different colors, which shows that they have a certain size. And so I started decorating the microgels with the gold nanoparticles. So that's in this video, you can see some small particles moving around. The dark spots on them are actually the gold nanoparticles. The hydrogel itself, they're basically water, so it's very hard to see them, but you can identify the particles with the tiny black spots here. And you can see that the decoration of the gold nanoparticles, it's not very uniform yet. So this was just the first experiment. So right now we're trying to optimize the coating and see if we can get uniform structure. So from here, we really have to do the self-assembly experiment and the photostimulation. So the idea is that we'll use a microscope. I have ordered an inverted microscope. So hopefully by the end of summer, I'll have these experiments going. And we combine it with a light patterning device, which is a digital micromirror device. And then we'll shine light patterns on our self-assembly. And I'm also trying to build some simple molecular dynamic simulation of self-assembly to basically try to explain what we observe in the experiment. And for future works, so as you can see that if we make these colloidal particles that have many interesting behavior, it can open up many different fields. For example, another field that people study is a thermophoretic motion. So you can also use this as active colloids. So what I'm really interested in understanding if we can couple this shape and motion and what kind of out of equilibrium physics we can understand. So if any of this sound interesting to you, please feel free to reach out to me. Here is my email address, and I'll be happy to take any questions. Thank you.
Thank you, Nabila, and we'll have a Q&A at the end of the session. So our next presenter is Natalie Schaal from State Northridge from the Mechanical Engineering Department. Natalie.
All right, hopefully y'all can hear me. Let me make this big. Okay. Let me see. All right. So thank you, Dr. Gomez, for the introduction. So as you said, I'm Natalie Schaal, and I'm Assistant Professor of Mechanical Engineering at CSUN. Looks like all of us presenters today are in the same area, so that's a cool coincidence. In terms of a little bit of a personal introduction, in terms of my institutional history and described via logos from my bachelor's to now, I started out at the University of Portland in Oregon, and then I spent a year at the University of Stuttgart in Germany, and then I did all my graduate work at Caltech, so I was there for a while. And then afterwards, I jumped into a professorship at Loyola Marymount University, also in LA. And then I started at CSUN almost 2 years ago, so fall 2021, and still here, of course. So a little bit more about that. So I actually grew up in Portland. So I was there a long time before doing my bachelor's there. And then, as I mentioned, I've been in this area for quite a while through the last 3 logos here, so a little over 10 years. In terms of a couple fun facts about me, if it counts as a fun fact, I'm a mom. So I have a son who's almost 3. He'll be 3 this month. And then admittedly, I am a chocoholic, dark chocolate only, please. But I really love chocolate and baking dessert. So I hope that these images of food don't distract you too much. I know we're getting closer to lunch. So for my plan for this 10 minutes is to have a pretty high level kind of zoomed out discussion of my research activities. I want to kind of throw out some keywords and ideas to kind of get us started with that. So I am very curious. I'm interested in a variety of fields, and it's hard to kind of package it together, but I'm trying to. So I would consider all of my research to fall within applied mechanics or solid mechanics. And then I also have a branch that's engineering education and kind of mixed with psychology. So of this list of my 4 main areas, the 2 highlighted ones, so number 1 and 3, are the 2 topics I'm going to discuss a little bit more today. So I won't discuss them now. Instead, I just want to give you a little taste of the other 2. So the second one here, improving student persistence in engineering. So this is the engineering education realm. A few different activities in that, some involving trying to better understand engineering identity and how we form that identity. Other projects involving interventions, educational interventions like peer mentoring programs and how that can, boost your sense of belonging and motivation to persist. And I'm currently involved in a project to develop an undergraduate research center at CSUN. Supported by NSF, as faculty mentored research is a high impact practice. So we're trying to get that off the ground, and we're launching some surveys soon. Item number 4 here. So this one, non-destructive evaluation and structural health monitoring. This umbrella also involves a few different projects over the years, some fatigue related research, some ultrasonic damage detection. And then currently we have a project with NASA related to this live dynamic monitoring of this vibrating structure. So that's the kind of the little bit introduction to me in a scientific sense. So then let's go a little bit more deeply in the first project about earthquakes that I haven't talked much about yet. So here I just wanted to start with kind of what my typical motivation is in any earthquake related project that I work with. I'm definitely motivated by foreshocks and the idea of a potential for someday to have a mechanics-based earthquake forecasting method. So as we all know, earthquakes pose a great threat to people and property around the world. But what you might not know is that how earthquakes nucleate, so that just means initiate, how they start, is a fundamental question of earthquake science. So of course we have different theories and ideas, but we don't fully understand it. And if we can better understand how earthquakes start and the relationship between different earthquakes, then, right, we may be able to increase our capacity to protect human life. So in terms of what it would take, at least from my scientific perspective, to be able to produce some earthquake forecasting method, I have this arranged into 3 ingredients like you were cooking. Right. So ingredient 1, to answer these sort of research questions. So why are foreshocks observed sometimes, but not always? So foreshocks are these smaller earthquakes that happen just before and right next to the big earthquake that follows. So we don't really know. With that, we also don't know quite how to model foreshock sources. So this was what my PhD was about, was actually testing out different models and seeing if they make sense. Ingredient 2, we don't fully know the relationship between these smaller scale events, these foreshocks, and again, the big scary earthquake to follow. So there's theories out there, but there's no consensus. So what is the role of foreshocks in the nucleation, the initiation of the big one? And then ingredient 3, can we identify seismic events? That's another word for term for an earthquake. Can we identify earthquakes as foreshocks before the main shock happens? So we would need to know this event happening today is a foreshock, meaning it has, precursory or forecasting power. We have to know that now. We can't know it after the big one's already happened. Otherwise, we've lost our chance to forecast. So these are just some key ideas to keep in mind in this direction. In terms of the scope of this work, it's all numerical simulations. So we simulate sequences of earthquakes. I'm particularly interested in fault heterogeneity, so some unevenness of the properties on the fault that makes things interesting. So different frictional properties and things can be uneven. For those of you closer to this field, maybe wanting to know about the simulations a little more, so they are fully dynamic and they run with a rate and state frictional framework, which is how we govern the fault. So at the end of the day, what I do is I'm analyzing the source behavior of the earthquake. So a lot of physics, geophysics in that, and mechanics, and trying to draw inferences about real earthquakes, see what this can tell us about real phenomena that we observe. So switching gears, jumping ships to a different direction. So this direction in trying to look at friction, and that's under the umbrella of tribology, so friction and wear, and a little more traditional engineering, so looking at engineering materials, just generally saying modern or advanced engineering materials. So this direction is actually pretty new for me. So this is something I'm trying to establish and design experiments and get the ball rolling from scratch. But in terms of why modern engineering materials and what that means, motivation here. So in engineering, we're constantly designing new materials, and a lot of those materials are classified under the umbrella of composites, meaning materials made out of 2 or more components, and they are constructed in a certain way to achieve certain desired properties, maybe a high strength, but a low weight, something like that. And so we're developing these materials for a specific sort of, usually like a strength sort of purpose, or maybe some anti-corrosion or something like that, but we don't fully understand the frictional or tribological properties. So we need to catch up in that. And in addition, if we don't fully understand those properties, not only are we losing energy and therefore also money from the friction and the wear, and potentially also fracture, but we're also limiting ourselves in the applications of these materials because we don't fully understand how they work. So with this idea of, again, it's kind of in the early hatched stage, but with my idea here, I want to develop experiments. I want to bridge the gap between what I know about friction and heterogeneity and instability from my earthquake work, and actually use the rate and state framework there to characterize materials over here and more in traditional engineering, but in the lab. So these composite materials, like other advanced materials, like 3D printed materials and things, are inherently heterogeneous. So I had that similarity there and want to, again, sort of bridge the gap. With that, again, the experiments within this framework, I'm in the process of trying to purchase a system to get started, some tribological system to conduct the tests. And again, the idea here is pretty open to the type of materials, as long as they're something new that we need to better understand, and something heterogeneous. And so the idea here, this is just a classic rate and state sort of properties, so we can try to characterize this sort of thing in the lab. So kind of to wrap things up, so again, in terms of the 2 highlighted projects, I'm open to any and all collaboration opportunities, but if I had to try to think of some specific cases for the earthquake side of things, maybe someone in seismology would be great, because that they observe natural earthquakes, they're dealing with those real practical limitations, whereas I work in a fantasy world, doing simulations. It's not necessarily something real. So if we can bridge our 2 perspectives, that would be very valuable. On the engineering material side, again, completely open. 2 ideas here would be maybe working with a material scientist to really get into the nitty-gritty of that, or someone who's a stronger experimentalist than me, because I'm kind of in both worlds, to help design the experiments. So with that, this is my last slide. Just, you've seen this one before, just to back out and say again, even though I've only highlighted 2 projects here, I'm open to collaboration on any of my 4 topics. You have my email address, and I'm looking forward to the Q&A session. So thank you for listening.
Thank you, Natalie, for an interesting presentation. Much appreciated. Our next speaker is Brenda Andrade from my previous campus, Cal State LA, from the Department of Chemistry. Brenda.
Thank you, Frank, for that introduction. Like Frank said, my name is Brenda Andrade, and I'm an assistant professor at Cal State LA in the Department of Chemistry and Biochemistry. A little bit about my background. So I actually did my undergraduate and master's degree at Cal State LA. And then I went off to University of Illinois, where I did my doctorate in chemistry in the Department of Chemistry, working on polymer chemistry. And then I also did a postdoc at UC San Diego at Skaggs School of Pharmacy and Pharmaceutical Sciences, doing research there on pharmaceutical agents. And the topic of my research is supramolecular chemistry. Supramolecular chemistry is the chemistry where we design molecules that can assemble into larger functioning molecules. A great example of this are soaps and detergents. The molecules that make up soaps and detergents have 2 different domains. They have a water-loving domain or a hydrophilic domain and a hydrophobic domain. These, or water-fearing domain. These properties give them the ability to assemble either at air and water interfaces because of their different properties, and then also assemble into these spherical droplets with oil inside of them and form these interfaces between oil and water. The supramolecular molecule that I'm interested in working with and harnessing their abilities are cyclodextrins. Cyclodextrins are actually products that exist in nature. They're created by enzymes that are in bacteria when they chew up starch. And they have, just like surfactants, different types of properties. So they have a water-fearing core, and then they have a water-loving exterior. And then they have two phases, a secondary phase and a primary phase. And these different properties and sites give them the ability to be able to be tuned for different types of assemblies. One application for this type of structure is actually capturing other molecules within their core, especially water-hating or water-fearing molecules. So these are commercially used in products like Febreze. So the way that Febreze works is that it will release a fragrant molecule and encapsulate the odor molecule and basically neutralizes the odor. They're also used in food products. They reduce the browning by capturing molecules that cause the color change in different foods and also preserving the foods. And then they're also used in pharmaceutical agents by solubilizing drugs that are not very soluble in water and then making them more bioavailable. The area that I would like to be working in is actually using these supramolecular containers as sequestering agents. Already there's a mounting work that is looking at removing toxic agents in vivo and in complex environments. These supramolecular containers are either cyclic, so they're round, or they're acyclic, so they're cleft-like. And they have different chemical versatility. That means that they have different groups that you can attach different things to them to build compatibility with the things that you're trying to sequester. And for a number of these different agents, they've been shown to be non-toxic. One of the key main successes in this area is actually a drug that's given in the area of anesthesia. So Supramolecular is a cyclodextrin derivative. So it's a cyclodextrin that has different groups on the outside, and it is able to reverse rocuronium, which is a neuromuscular blocking agent. So it basically paralyzes you. And so here's the structure of the Supramolecular, and then these purple groups on the outside are actually these thioethers that have been linked to the one side of it. And then the interactions between the charges of the drug and the charges of the linker are what hold the drug inside of it. Just like this, I want to do some research on how we can reverse engineer these supramolecular sequestering agents. And so I will be investigating the relationship between the changes on the chemical structure and their ability to sequester specific molecules. And my working hypothesis is that the site, so where I position the different modifications, and also the number of the modifications that I make are going to increase the affinity and the selectivity of these agents. So two current aims that I would like to address are using these to reverse engineer a cyclodextrin that can sequester fentanyl. Fentanyl is one of the leading opioids that is causing lots of overdose deaths. And the current treatment, Narcan, is good, but it's not good enough to deal with all of the different variants of fentanyl. So fentanyl has 3 domains, and you can make chemical changes in domain number 1 and domain number 2 that change their properties that can lead to the ineffectiveness of Narcan. So because of these designer variants, designing a cyclodextrin derivative that can target fentanyl and a number of its variants would be very powerful as an overdose countermeasure. The second area that I would like to focus on is pesticide removal. DDT is an insecticide that was banned back in 1972. It's very harmful and it has carcinogenic effects from humans. Recently, there was a discovery that on the coast of Southern California, there's a number of deep ocean disposal sites. And so designing molecules that can bind to these and get them out of the environment would be very, very useful and very powerful tool to be able to mitigate the damage that these agents can cause. So potential collaborations would be to work with people that actually collect soil samples that have pesticides in them, or people that work with opioids in mice or in human samples to put my agents to the test. So I'm open to answering any questions, and I look forward to talking with all of you.
Thank you, Brenda. Very interesting presentation, and it's always nice to see a fellow Cal State LA graduate alumni. So
Thanks.
I now open it up to the audience for any questions they may have of the speakers, and speakers can also ask questions of each other too. So I'm trying to move away from the one screen here. I just see Brenda on mine, but any questions out there? Well, yes, done.
Well, my question is for Nabila. That, I want to know if he has considered Faraday instability in her studies.
Sorry, excuse me, what stability?
Faraday instability, it is when you have a liquid surface and then you vibrate this. It will create some kind of pattern, shapes, because, you mentioned that shape change, it is very interesting. I want to know if it is interesting to you.
You want to vibrate, you want to shape change like using vibrate, like ultrasonic?
No, it is normal vibration, mechanical vibration. It's not ultrasonic.
I see.
Mechanical vibration.
Yeah, I mean, if you just use mechanical vibration, you can use that to drive a structure out of equilibrium, right? I guess.
Yes, exactly. I have the equipment, I work in San Jose State University. I have the equipment here. I can do the experiment. But the question is, are you interested in collaboration?
Yeah, sure. I would love to talk to you more about it. So what kind of length scale? What's the length scale that you're talking about? How large particles?
Well, it is like something, it can be as big as something. It is aspect ratios, we are talking about aspect ratio, but it can go something like, I have done many tests before, something like 10 centimeters diameters. But the problem is how much liquid you will put there. The height of liquid is very important.
I see. Okay.
But I think we will talk later about
yeah,
that.
Yeah, thank you so much. Yeah,
I will send you email. Please, if you have anything, please respond back, because in many of these sessions I send email, I did not respond, get any response. So please respond to me. Thank you.
Yeah, of course. Yeah. Yes, I'll think about it a bit more. Thank you.
Thank you.
Questions? I have a few, but I
Can
don't
we
want
go through the ones in the chat, maybe, Dr. Gomez, from Dr. Zitterman?
Yeah, I spared you my rambling, so I just posted them. Tom here.
Okay, Natalie, why don't you start off, and then we'll go to Brenda.
Oh, okay. So thank you for the question. I think maybe I wasn't fully clear on what I meant by a mechanics-based forecasting method. I meant a method that's based on our understanding of the mechanics of how earthquakes work. So about the stress and the slip and the relationship, not something as like a mechanical, not like a detector system. it's more about a mechanics in terms of physics understanding. But to kind of discuss something related to that, so in terms of trying to measure something and say something about earthquakes, there are early warning systems. So you would, with a seismometer, actually detect a wave that's radiated to you and say an earthquake's happening here. And basically you just do a time of flight analysis to say, okay, if the earthquake's here, the waves radiated from that shake the earth travel at a certain speed, and I can give you a few seconds or maybe a minute of warning of before the shaking reaches where you are in the city over here. So that is sensor related, but that's an early warning. It's not a forecasting system because an earthquake's already happening. So it's kind of too late. You can get some warning to maybe get out of the building or something, but that's one thing. But the point is that more of what I'm referring to is in terms of trying to forecast, I think about like the weather to say tomorrow it's going to be sunny and it's going to rain or not rain. That's what I mean. And for that, we don't have any way to do that because we don't understand the mechanics of earthquakes well enough. If you hear any forecasts or predictions out there, they're basically all statistically based. So it's just saying, well, this fault has a history of events of this type and things like that, and saying, oh, probably just based on the math of it, we think maybe an earthquake's coming in a certain time frame, but it's statistics based, it's not physics based. So long story short, I want to be able to say, like, an earthquake happened right now, a small one, maybe a magnitude 3, and because of my better understanding of mechanics, I know that this earthquake is a foreshock, and I know the relationship between foreshocks and main shock, so I can forecast that a main shock is coming next week on Tuesday at 4 p.m. of this size, and we can prepare, days or weeks in advance for that. I'm sorry if I wasn't clear in my presentation, but I appreciate the question.
I got it. So follow up. So if you understand the mechanics, could you do geoengineering to mitigate and prevent earthquakes?
Do you mean in the realm do you mean like inducing earthquakes and things like that? Like forcing them to happen or trying to stop them from starting?
I guess both. Yeah, if you could induce tiny ones that aren't destructive to release the stress, then you'll prevent the big one.
That is a topic out there. So when it comes to like fracking and things like that, anything that changes the pressure and things in the earth, you can induce earthquakes, even accidentally, right? So there is a question out in the field on whether we can do it purposefully, exactly as you're saying, make a whole bunch of tiny ones, relieve the stress on the fault, and hopefully never get a big one. That question is out there, but I think for the most people are too afraid of it because it's playing with fire. What if you're wrong and you accidentally trigger a huge one? So no one's really, as far as I know, but I clearly don't know everything, no one's really going there yet. And I think part of that is, again, we don't fully understand the relationship between different earthquakes happening in the same region. So we're not ready to play with fire.
Good caution. Thank you.
Yeah.
Real quick, I want to tell these short stories and prediction of earthquakes. One of them had to do with when I was in grad school at UCLA. I was up on the 6th floor of the chemistry building, and I was listening to the radio, and the radio station was based in downtown. So I remember the announcer goes, we're experiencing an earthquake. We're experiencing an earthquake. And at UCLA, I hadn't felt it yet. So I sat down because you can't get out of the building quickly, okay, especially on the 6th floor. So I sat down and counted 1,001, 1,002. It took 5 of those. And then it came. And I swear on the wall, you saw the ripples of the earthquake as it passed me by. It was like really funky, okay, to see the ripples of the waves go by me like that, and all the stills and everything were just like swooshing and swooshing like that, which was pretty crazy. One last quick story is we were having, I don't know, 7-8 years ago, a few cluster earthquakes in SoCal, and I remember being sitting down eating some late lunch, and in my mind, I thought, oh my God, we're going to have an earthquake right now. And I swear, about 30 seconds later, we actually had an earthquake. So it was just real weird. I had this kind of weird sense about that. So before we get to Yazdan again, I would like to go to Brenda and then Tanjeem to kind of go through the questions that Thomas had.
Yeah. To answer the carbon dioxide question, so there are people that are working on capturing carbon dioxide using supramolecular chemistry, but they're using MOF. So metal organic frameworks are another form of supramolecular chemistry. So basically they take metal, like ionic metal, and then they take organic ligands and they can assemble these porous materials, and the carbon dioxide can get captured in those pores and then later released. So that is a technology in supramolecular chemistry that is being used for that. I don't know of any people that are using cyclodextrins, but theoretically you could attach metal centers to the framework and use it as a carbon dioxide capture agent, theoretically. But I don't know of anyone that has ever done that. Cholesterol in the blood is actually, I did answer the question, but if anybody else is interested, there are companies that are working to use cyclodextrin. I'm not sure if it's like dietary like cholesterol or if it's in the blood, but cyclodextrin, the native ones without any functionalization, do capture cholesterol very strongly. And actually that's one of the reasons why we don't use native cyclodextrins in the blood, is because it can sequester cholesterol from your cells as well, if you have a high amount of it. So the derivatives are probably better for any application within the blood.
Great, thank you, Professor.
Yeah.
Nabila?
Yes, so what wavelength? So the gold nanoparticles that we have made so far, the absorption peak is around 530 nanometers. So it's very much invisible green light. And the spatial resolution, so it depends on the size of the microgels that we make, right? So we made about 2 micrometers. So the smallest that we need to project is 2 micrometers, but it can be larger than that because the prediction that I have shown that the theory, they have actually project an area of the self-assembly. So maybe like 10 or 15 particles area, but the smallest you want to address is 1 particle size, and it's still 2 micron is not diffraction limited. So I believe it's very possible when you use like a high numerical aperture objective.
Did you say 5,000 nanometers? That's in deep IR?
No, 530 nanometers.
Oh, 530. Okay, thank
Yeah.
you.
Yazdan, and then Natalie.
Thank you. I have my question for Brenda because, about the molecules she talked about. I want to know if she has used this for two-phase flow, or better said, it is gas condensate reservoir. Because I work in some application in my postdoctoral to increase gas production. So it was very important to have some molecules that could increase the gas production. So, meaning that the water would not pass, but gas will pass. And also it was in porous media because, reservoir are in porous. Thank you.
Right. Yeah, I was trying to get more information about the type of gas you were thinking of. Is it methane or carbon dioxide, or what types of gases? Or are there like short hydrocarbons that you're thinking of?
Hydrocarbon. It is the gas that we use in our home.
Oh, like propane.
Propane, yes.
Yeah. I guess if you made, so there are cyclodextrin MOFs, so metal organic frameworks, again, this idea. So you can make those and you can make porous materials. And then there's also cyclodextrin polymers, so you can attach them to a polymer string and you can make.
Yes, Brenda, I have done this. I have worked in labs,
I see.
some experimental method. I want to know if you are doing some of these things.
Oh, no. So right now I'm only looking at capturing small molecules and not making the porous materials. I do have the training and background to be able to do make these types of materials, but at the moment I'm focused on tuning the different derivatives to strongly and selectively bind small molecules.
Thank you very much. Thank you.
Natalie?
Sure, thanks. My question's for Nabila. I think that your project's really cool, and from a fundamental, just mechanics and physics perspective, I can see that the value in exploring it. It seems very exciting. From a sort of engineering or practical perspective, I'm very curious about ideas for the applications of this, like even the little kind of micro gripper robot, right, that can grab a cell, like you said, and then you can use magnetism to pull it away. Like, what are some applications of that? Is that all in the medical field? Could that become? And then with your particular project, designing these systems to be responsive to light, what are potential applications with that as the trigger? I'm just very curious about what this could become a few years from now.
Yeah, great question. So the video that I have shown, so that there's a group at Johns Hopkins, I believe. So they use this kind of structures they're trying to explore actually doing something medically useful, like a biopsy. So you want to collect cell samples without actually cutting your body, like doing invasive surgery. So yeah, I mean, that's like to me, that is the most exciting application, like minimally invasive medical procedures. But then of course you need to start thinking about like what kind of biocompatible materials you want to use, right? So that will become more of like involve like material science problems. Yeah, as far as like self-assembly goes, so one advantage of that, you have the capability of like potentially disassemble a structure. So if you don't need it, you can just like disassemble and hopefully get rid of that somehow. So I think that's an advantage. But I mean, it's still, I mean, because I'm a physicist, I don't think a lot about application, but I'll be like interested to, look at it more. And that's one, like, I guess my collaboration, what I'm asking for is like, if you have any interesting application in your mind, and then we can maybe like take that kind of approach. It's like, okay, what do we actually use it for? Thank you.
Physicists should always think about applications. That's kind of my view. I do have a question for you, Nabila. My work's in microfluidics, and we used to do a lot of work in binding and assaying and what have you. And we're playing with a little bit of some nanoparticles too. So is there a way that you could change the shapes of particles, but actually into shapes that you want? I don't want kind of generic, like they're squished or they're elongated, but we can actually target a design or a new shape that you want based on how and this is, I think it's a chemistry question too, and I don't know if that's possible. And the second part had to do with in these nanoparticles with the gold nanoparticles and the colloids. I think you mentioned was it 530 excitation?
Yeah.
Okay. So have you looked at other types of nanoparticles that one could control at other wavelengths of light? Because not everything is amenable to, say the visible spectrum per se.
Yes, of course. So the first question was like different kind of shapes, right?
What specific defined shapes, not like
yeah.
you wanted to get chubbier. That's kind of, that's multi-directional, but
so that kind of research is all done a lot in the larger scale, like a couple 100 micrometers. So the shape changing pasta example that I gave, right? So the way they do it is using photolithography actually. So if you can pattern different kind of shapes, you can then like just have like a shape output in mind, and you figure out what the input would be. So it's that kind of work is being done in the larger scale, and you can imagine like I'm talking about colloidal particles, so it's difficult to do it with photolithography. Maybe with microfluidics you might be able to use it, right? If you like use, I know some work has been done in like MIT's different particles, hydrogels with different materials, right, with different layers. So it comes down to more of like both like engineering and also like figuring out from shape to shape A to shape B, and you want to do it in 3D. So yeah, so that's I think it's still ongoing work. And about the wavelength, I mean, of course, you don't have to necessarily be using gold nanoparticles. Even if you use gold nanoparticles, you can change the aspect ratio of the gold nanoparticles to make it gold nanorods. So then that become like IR sensitive in infrared. And you can use other photoresponsive materials also, like azobenzene and so on. So there are all sorts of different materials that people use. So I just chose gold nanoparticles because it's easy.
Yeah, because they're easy and everybody uses them. Yeah.
Yeah.
Okay, I appreciate it. Yeah, Yazdan.
Oh, sorry that I'm asking. Can I ask this question? This is the last question that I have. And it is for Natalie. Natalie, I have a question. Because you mentioned that you are working on improving persistence, and I'm working on STEM. My question is that, do you have any references or any fields for improving persistence? So what you're working on that, would you please a little bit talk about that?
Sure. Yeah, there's a lot of different, in the literature, there's a lot of different interventions that have been proposed and other people have tried, and some are gaining traction. So there's basically a lot of variety of options to choose that you can take and try out yourself. But basically, a lot of it does have to do with sense of belonging, right? I study student persistence, specifically focused on broadening participation in engineering. So that may be for women, that may be for minoritized students, first generation students, things like that. So if I don't see myself in the faculty, if I don't feel like I'm part of this community, if I always feel like an outsider, then psychologically I'm much more likely to leave because I don't feel like this is my home, my place. So basically, most of the interventions are centered around trying to strengthen that sense of belonging. So you do belong here and you are valued and you can do this. So that can be things in the class, different changes in pedagogy. That can be things like I've tried with peer mentoring, or even having seminar series on show you different examples of how your engineering degree can be used that isn't traditional. Like my friend works in visual effects and he has the same degree that I have, right? Just to make straight up mechanical. So trying to broaden the options. There's so much I could say about it in so little time. So unfortunately, that's just the taste of it. But there's in-class interventions, there's out-of-class interventions, and just overall changes that can be made to warm the chilly climate of STEM, as it is so fondly known.
Okay, thank you very much. One question that I have you ever tried an ice-breaking aspect to do something like this?
Yeah, so one of the recommended strategies in terms of pedagogy is to start any class, regardless of topic, with something that has nothing to do with the class topic, right? So introducing yourself as a faculty, that even the fun facts about yourself, getting to know the students, their interests, their hobbies, all that sort of stuff, because that recognizes everyone in the room as a person. We're all people, right? And getting that bond created is very helpful. So then later down the road, when students have a question about the course content, they feel comfortable approaching you because they feel seen. So that, yes, icebreakers definitely help.
Thank you very much. And my last question, it is about numerical simulation on earthquake that you mentioned. That what kind of numerical simulation you use?
So the method for my PhD code, it's the spectral boundary integral method. So since a fault is a boundary, we're studying that action on that boundary. I'm also currently involved in a project, a collaboration with another university, where my colleague's code is a hybrid code. It's spectral boundary integral combined with finite elements, so you can actually discretize some space off of the fault as well. But my PhD code is gigantic, which is a problem because you need a supercomputing cluster, and it's very parallelized, and it's a very expensive code to run, which is trouble, but I'm working on it.
Do you think it will work on International Space Station?
I'm not quite sure what you mean by that.
What I mean is that when you have residual vibrations, and then it can create some kind of movement. So my question is that, do you think it will be applied to that kind of environment? And if I can define the residual acceleration.
So the code that I have isn't about the waves that are radiated. It's not actually about the vibrations that are produced. It's just about geomechanics of what's on the fault, the stress distribution, how things are slipping, the velocities look. I study the sources, not so much the radiated waves. We just want to understand what's happening at the source as a starting point.
Oh, okay. So, you know, the source, for example, the source that you are mentioning, it is residual acceleration or body forces that I can redefine there. For example, something G0 sine omega t.
You can take the action on the fault and then calculate the waves that will be radiated and how those go to shake, but that's not quite what my simulations do or what I study.
Okay, I will send you email. Thank you very much.
Okay, thank you.
Okay, well, thanks for everybody to be on today's virtual cafe. Very interesting dialogue. And I think Yazan asked, if you just do a scholarly search on persistence in STEM, you'll have more articles than you do have hours in a week that will take you to read. And it's the same thing with a sense of belonging and STEM. Add another couple weeks for all those articles. If you look at really just a lot of background on the NSF IUSE and HSI STEM grants that have been funded both within the CSU and outside the CSU, a lot of them really focus on just different variations of, may it be STEM identity, sense of belonging, persistence, motivation, expectancy value theory, culturally responsive pedagogy, critical race theory. And it's almost like they're running out of things to study because they've studied this. I guess it's more in the interventions. What do we really want to do that is transformative and novel that may have a spin on any of those things that I mentioned that hasn't been done already? So with that being said, thanks everybody for attending today. Have a great weekend and a safe one. Take care. Bye.